Hello everyone, let us do one more numerical problem based on electric flux density. In the question, we are asked to find electric flux density at a point P due to a point charge, a uniform line charge and a uniform surface charge. So it is similar to the earlier problem which we have solved. We can do it quickly. So let us consider a point charge of QA, which is of 55 millicoulomb present at minus 2 comma 3 comma minus 6, and the point at which we have to find flux density has the coordinates 2, minus 3 and 6. We should find what is the vector from charge to the point P and then estimate the flux density. Rp vector is what we should find. So it is 2 minus of minus 2, it is 4 ax cap, and minus 3 which is minus 6 ay cap, and 6 plus 6 which is 12 az cap. Flux density d vector due to point charges q by 4 pi into vector rp divided by rp cube. So we should find magnitude of rp, which is under root 4 square plus 6 square plus 12 square. We can compute using calculator and see. So under root 4 square plus 6 square plus 12 square, so which is 14. And we can make the substitutions in vector d to get d due to point charge, which is 55 milli divided by 4 pi into vector r is 4ax minus 6ay plus 12az divided by 14 cube. So we can do that in the calculator. So 55 milli divided by 4 into pi into 14 cube. So this has to be multiplied with 4 for the x component, which is 6.3 micro. So I will be getting vector d 6.38 ax cap. So entire thing I will write in 10 power minus 6. So x component is 6.38 ax cap and y component should be multiplied with minus 6. So this should be multiplied with 6, 9.57 micro. So this will be again minus 9.57 ay cap. And for z component, this should be multiplied with 12. So it will give plus, I should give in micro. So let us give 19.14 micro plus 19.14 az cap. And the unit for flux density is coulomb per meter square. I can write this 10 power minus 6 as micro coulomb per meter square. So micro coulomb per meter square. So this is for the first subdivision, which is for the point charge. Next, we should do for the line charge. We can repeat the process and do for a line charge separately. So let us try to understand the line charge equation and the position, etc. So the line charge is on x-axis. Let me consider x-axis. Equation of x-axis will be given as y0, z0, and x can take any value from minus infinity to plus infinity. It has the charge density of 20 millicoulomb per meter. So the formula for flux density due to line charges, rho L by 2 pi vector RL by RL square. So the point at which we have to find flux density has the coordinates 2 comma minus 3 comma 6. So first we should draw a perpendicular from P to this line charge. The point of intersection we should find, coordinates of P dash we should find. We know always on x-axis y coordinate is 0 and z coordinate is 0. X coordinate will be same as the coordinate of the point P. So because we have drawn perpendicular from the point P, so the coordinate of x will be same for the point P and P dashed. Now the vector RL is from line charge to the point P. We can write what is this RL vector. X component will get cancelled. Y component is minus 3 AY cap plus 6 AZ cap. And we can find magnitude of this as under root minus 3 the whole square, or we can simply write 3 square plus 6 square. We can compute using calculator, that is root of 3 square plus 6 square, which will be 3 root 5 or 6.7. So we can write this as 6.7 and make all these substitutions to get flux density. Rho L is 20 milli divided by 2 pi and 6.7 square multiplied with vector R is minus 3 AY plus 6 AZ. So we can make use of calculator and do the computations quickly. That is 20 milli divided by 2 into pi into 6.7 square. This has to be multiplied with 3. So you'll get, let me represent this in micro as well. So 212.72 micro. So the y component is minus 212.72 micro. So everything let us give in micro. This is y component. To find the z component, we should multiply this with 6. So that gives 425.45 micro. 425.45 AZ component micro. So this entire micro thing we can represent as 10 power minus 6 thing we can represent as micro coulomb per meter square. So this is the flux density due to line charge as per the given question. And the last thing what we have to do is for surface charge. So let us try to understand where is the location of the surface charge and find flux density. So the surface charge is located on z equal to minus 5 plane, and the point P has the coordinate 2 comma minus 3 comma 6. So this z value, the plane of surface charge is z equal to minus 5 and this value is 6, which will be lying above this surface or above this sheet. So point P will be lying above this sheet, and when we try to write the formula for flux density due to surface charge, it is rho s by 2 a n cap. When we try to draw the flux density vectors from the sheet to the point P, it will go in positive z direction. I can write a n cap as positive z direction. Thereby, we can make the substitutions. Rho s value is 120 microcoulomb per meter square. Surface charge density is 120 microcoulomb per meter square. I'll write it as 120 micro divided by 2, and the direction of flux density to the point P is positive z direction, which will give me 60 AZ cap microcoulomb per meter square. This is the flux density due to this surface charge. So you can practice many problems based on this electric flux density due to line charge, surface charge, and point charges for better understanding. Thanks for watching.